Okay. So let's start off with the basics of NMR. So what we're going to be doing in this class is called hydrogen NMR. So basically it's nuclear, gosh, I'm going to completely butcher this. Nuclear magnetic resonance. So basically it's based on like the magnetic fields that are produced by hydrogens. Um, And so like we can use it to kind of figure out how many hydrogens are in a molecule, and then you can figure out the location of the hydrogens and then figure out the basic shape. There's also certain peaks that are going to be associated with like hydroxyl groups, carbonyl groups, blah, blah, blah. So that'll all be really useful to know. There's different kinds of NMR, but we're just going to be doing mostly like in orgo classes, they just do hydrogen NMR. Um, okay. So there's first off, when you see your NMR like graph, it's gonna range from 0 on one side all the way till, I don't know, however much on the other side. So the x-axis is basically gonna be numbered, and we see different things at different points in the x-axis. But that's actually not the most important thing that we're going to be using. I know when I first heard this kind of stuff, I was really, really worried because I was like, oh my God, I'm going to have to pay attention to where it's located on the x-axis. But actually, you're not. I mean, you will to a certain extent. Sometimes you'll have to, but mostly you won't. So there's like a whole bunch of lecture stuff, blah, blah, blah. But I kind of want to start, like, skip to the really important stuff. So first of all, we are going to have um, something. So there's one signal that you'll always ignore pretty much at 0. It's like a little, like, let's say here's our x-axis. There's going to be like some signal here at like 0. Ignore that. We're going to ignore everything to the left of that. We're going to pay attention to everything to the left of that. So there's a few different things we're going to look for. So there's singlets, it's going to look like that. There's doublets, which are like that. Then there's like triplets, which are like this, right? The quadruple one, which is, oops, like this, whatever. So basically, it's all about the number of peaks. So this is a singlet. So inside, we're going to write S and then like a bracket around that. Okay, and this is a doublet, which is a D. This is a triplet, which is a T. This is a quadruplet, which is a small q. Because we're also going to have, I believe, 6. No, I don't know. There's going to be like a large q too. So that's all going to be really important. So, also, are you guys on the notes from October, from February 6th? No, February 9th? Yeah. So we're starting with that, but we'll probably move on to the 16th real quick. Um, oh yeah, so that's a quartet. Then there is a quintet, which is basically 5 of them. So we'll call this a pentet. And then there's a sextet and a septet, but like we barely ever get there. Mostly we'll be dealing with singlets, doublets, and triplets. So what those tell us is that that is the number of hydrogens in that position. So a singlet means there's 1 hydrogen there. Doublet means there's 2 hydrogens there. So let me just give you a basic example of what this will look like. So like if I have something like this, there's 3 hydrogens on the right. 1, 2, 3. So that would look like a triplet. That's your classic triplet. We kind of know that's like a methyl, basically. And then for this carbon, there's 2 hydrogens, so that would be a doublet. So that's the basic principle of what's happening here. I hope that makes sense. Okay. So all this stuff like that he's talking about in the first lecture is not really that important. Like listen to it in like it's like an intro, but it's not really what you're going to be doing on the exam. So don't get worried if there's like a lot of different things going on. All right. So generally, let me just back up a little bit. So how will an NMR question work? So generally, he'll give you a graph. He'll give you a graph, and there's x-axis. there's a whole bunch of like things happening, whatever, whatever. And then he'll say, oh, this is like C6H12O. Oh my God, I'm doing C6H10BR, whatever. So he'll give you the molecular formula. So you need to use your molecular formula along with other things to figure out what the shape of that thing is. And I'm gonna, you know what, I'm gonna go ahead and let's go to page, okay, wait, let me see. Where does the first example start? Okay, let's go to page 5 of the review. Okay. So this is an example of toluene. So one thing that we need to look for that I should mention first is the cyclohexane. So you're going to get two different kinds of cyclohexanes. There is the para-cyclohexane and the meta-cyclohexane orientation. And you can tell that based on a few things. So on page 5, we have all the way at 7. This is where you look for your cyclohexanes at 7. So we have this whole thing. See, that's like the only like the one important thing. So once you get to around 7, 8 in that range, that's where you can expect to see your cyclohexanes show up. And so whatever you see there, there's a few different patterns we'll look for that I don't really want to talk about right now. But and they're not, because these graphs they showed right here aren't that good, which is one of the complexities of dealing with NMR. But basically, that's where you can tell where your cyclohexanes are, and it will tell you if your cyclohexane has a para or like whatever. Also, they're not just cyclohexanes. I should take that back. They're benzene rings, so they're aromatic. And then if you look all the way back, he showed a. God, this is not very clear at all. Oh my God, I completely forgot. Okay. Yeah, guys, this is going to be like a little bit of a learning curve for me too, because I completely forgot about what these peaks mean. So there's a singlet right here. Okay, what does a singlet mean? So a singlet means one hydrogen, but it really means one hydrogen over from the carbon. So when we have a toluene right here, there is this thing which has 3 hydrogens, but it is 1 carbon away from 1 hydrogen, right? So that's why it's a singlet. Do you guys see that? So it's basically about, it describes that there is a hydrogen, 1 hydrogen there. Okay, that's why it's a singlet. So it's saying that there's a carbon where it only has 1 adjacent hydrogen, because this carbon is only attached to a carbon with 1 hydrogen off of it. And in the next one, he gives you the number of hydrogens that are singlets. So, oh, okay. So basically, this singlet, he will say 3s. Okay. So that means there's 3 hydrogens that are all a singlet. So, so this is something, I'm so sorry guys, because these graphs are really like, he starts off with the worst graphs to teach you, and then when he goes on, the graphs get clearer and clearer. But like this graph, you can't even really tell that it's a singlet. It's like really confusing, right? So basically, what he will label this generally, like he'll label it as 3s. So what does that mean? It means there are 3 hydrogens that are all singlets. So there are 3 hydrogens. So let's start with that part. So the 3 hydrogens are here, 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 right? And they are all singlets, meaning that the next carbon over only has 1 hydrogen on it, which is this hydrogen right here. Does that make sense? I know it's like really like complicated and a little bit weird, but like you'll get really used to it, I promise. So it says 3s, which means 3 hydrogens that are all singlets. And then the peaks here at like 7, those describe the hydrogens that come off the rest of the cyclohexane. Really, it's going to be a multiplet, so you're going to see 5 to that peak. That's why, again, this graph is really bad, because actually, like, it's actually 5 of them, because there's 5 hydrogens in that cyclohexane, right? So, yeah, but you can't see it. All right, so for the next one, let's go on to one more example. So for the next one, he again has something around 7, whatever, like we can't really see what it is, but if we looked at it, it will actually only have four in it. So this would be a Q. So it has 4 in it, and that tells us that our aromatic ring only has 4 hydrogens in it. So those hydrogens like that, right? And then, oh my goodness, I messed up, guys. There's no hydrogen here. Did anyone see that? Oh my goodness, this is a learning curve for me too. There's no hydrogen there because it's aromatic. It has double bonds. So let me draw it with the actual bonds. See, there can't be a hydrogen there. That's no hydrogens. So I'm so sorry, guys. Singlet stands for 0 hydrogens. This is like, it's really weird that like I did this like a year ago, but it's like very, very rusty. Does that make sense? Does everyone see how that has 0 hydrogens on it? Okay, so it has 0 hydrogens, and singlet means 0 hydrogens. It doesn't mean 1 hydrogen, it means 0. Doublet means 1 hydrogen. So it's like 1 more. So if you had something like this, and let's say here there's 3 hydrogens, so this would be a 3 what? What would be inside my bracket? Would it be a singlet, doublet, triplet, what? In the chat. You have to look at the carbon adjacent to that carbon and see how many hydrogens are in that carbon. Yes. It would be a triplet. Exactly. So let's do this for all of these. Let's just for practice do this real quick. So this would be a 3 triplet because it's 3 hydrogens that are all a triplet because there's 2 hydrogens there. Okay, let's draw all of our hydrogens real quick. And then let's do this for the rest of them. So this would be, how would I describe this one in the same format that I did the other one? Okay, so I'm not really getting that many responses, so I'll do this one again so you guys can see. So this is 2 because there's 2 hydrogens, and this is actually not going to be, it's not whatever, it's basically going to be a sextet. And I can't remember how to denote a sextet. Like, I don't really remember, like, what number. And you can't make it an S because that would look like a singlet. Okay, does that make sense? Because adjacent to it, there's 2 hydrogens here and 3 hydrogens here. So add 1 more than that. So that's 5 hydrogens that are adjacent to it. Add 1 more, that's a sextet, right? Okay, do this one. Send me what it is in the chat. Yeah, it's a 2 sextet. Okay. Now what's this last one? Yes. No, it's not a singlet, it's a triplet. Because adjacent to it, there are 2 hydrogens, add 1 more, triplet. Okay. All right, so now that we've gotten that out of the way, let's continue with this next example. So this example would be a quartet. It would have 4, or how do we say Q? Let's see, 4. Yeah, quartet. So basically, this would be a quartet. It would have 4. Like that, because like you can't see that on the graph. So this would have 4, and what does that tell us? That tells us that an aromatic ring only has 4 hydrogens on it. So that means there must be something coming off of each end, right? We don't know what yet, but there must be something because only 4 of them are available. And then also something else that we'll talk about later will show us that these 2 things are para to each other. Because they could be, you know, they could be ortho, right? It could be like this. And that would still be 4 hydrogens coming off of the aromatic ring. But no, it's para, and there's something else that he would show along with this that would show you that it's para, a different graph. But for now, trust me when I say that it's para. So after that, you look all the way to the right, and there's a singlet here, and he says that this is a 6 singlet. 6 hydrogen singlet. So we know that there are 6 hydrogens that have adjacent 0 hydrogens. So that tells us these are each methyls. Does that make sense? Because there's 6 hydrogens, right? 1, 2, 3, 1, 2, 3. There's 6 hydrogens that each of them is basically in the same position on this molecule. So this also tells us there's symmetry in the molecule. You know what I mean? That's something that also lets us know it's para. There's symmetry in this molecule because it has 3 hydrogens here, 3 hydrogens here, and if you think about it, geometrically speaking, each of those hydrogens is exactly the same, right? They're all in the same position on the same molecule. So, that's how we kind of know it's para, because, like, if I had something else like that, but you guys don't need to know that it's para yet from that. There's another way to tell if it's para. So anyways, each of these hydrogens has adjacent 0 hydrogens to it, so that's why they're singlets. Okay, now here's another example. So I hope you guys are getting used to this by now. In this example, this would actually be a triplet, right? Or I don't know, whatever. This thing right here, it tells us that it is like this, and it only has 3 hydrogens off of it. So we're just gonna, you know, put those, we know that there's like X, Y, and Z coming off of the benzene ring. Also over here, there's a 9H singlet. So that tells us that there's 9 hydrogens that each have adjacent to 0 hydrogens. So now we know that these are just methyls, because CH3, 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 and if you look over the carbon next to it, there's 0 hydrogens on that carbon. Okay. Next, let's get into something a little bit more complicated. So here, this is page 6. He has 1, 2, 3. He has a triplet. Okay. And he has a doublet. All right. So from this, and also he gave us a molecular formula of CH. Oh, wait. I don't think you should have given that. Let's say, okay, yeah, he gave us a molecular formula of C2H3Br. Okay. So looking at this, we know that there's 2 carbons, and there's hydrogens coming off of those carbons, probably because we have 3 hydrogens. Some of the hydrogens are triplets and some of them are doublets. So that means some of them, doublet means that there's 1 hydrogen adjacent to it. So let me draw out my 2 carbons, right? C, C. So if, I don't know how to explain this. If one of them has hydrogens that are doublets, for example, that means there's only 1 hydrogen on the other side. And then this hydrogen on this side would be a triplet because there's 2 hydrogens on this side. So that's kind of what makes it have that situation where there's 2 on one side, 1 on the other. Because if you go through it and it's like, okay, this is a doublet, this is a triplet. So some of my hydrogens are doublets, meaning there's only 1 hydrogen across from it. So that must be it. And then some of my hydrogens are triplets, which means that there's 2 hydrogens across from it. So it's kind of like one of those like back and forth things. And then you really have to use logic to figure out these. After that, we know that there's also, 3 BRs. So that must mean that there's like a BR here, a BR here, and a BR here. And now you're done. So you have to use a combination of the molecular formula and your graph to figure out what's going on. All right, next. And for now, like, don't worry if you're not getting it at all. Like, I'm just going to show you guys stuff, and then you'll get it eventually. All right, here's another one. So here we have a quartet, and he tells us, sometimes he'll tell us when he does, that's really nice. He says this is a 1 quartet. And here he also has a doublet, and he says this is a 3 doublet. Okay, so, and the formula for this one is because he didn't give C2H6. No. Okay, so the formula for this one is C2H4Br2. Okay, so looking at this one, we can start off by just drawing our two carbons again. So we know that there's a doublet. Some hydrogens are doublets, so that means that there must be one hydrogen coming off of one of the sides. So that would make the hydrogens on the other side be doublets. So if we have one hydrogen, we necessarily need to have one hydrogen coming off of one of them. That means all the other hydrogens must be coming off of here. So that's three of them, 3 hydrogens. And that follows through because a quartet is from having 3 hydrogens on the opposite carbon. So this hydrogen is showing up as this. One hydrogen is a quartet. See, one hydrogen is a quartet. One hydrogen, that one hydrogen coming off the carbon, it's a quartet, i.e. the carbon adjacent to it is attached to 3 hydrogens. Because you add one more. This one, these 3 hydrogens are showing up as a 3 doublet, meaning that there's 3 hydrogens and they're all doublets because adjacent to that carbon, there's another carbon that only has 1 hydrogen on it. Okay. Can you guys let me know if this is like working at all? Are you following? Okay. All right. Next, let's continue with the rest of it. So there's 2 BRs, so that makes sense. It works out perfectly that we can just put those on here. All right. Next one. So for this next one, we have and like that information he wrote in pen at the bottom, he will give it to you or else it'll be super clear on your graph. Don't worry about that kind of stuff. Like in the beginning, I was really worried that like he would somehow throw random things. And by the way, notice how I'm always ignoring those spikes at 0. Those spikes at 0 are basically a way of calibrating the machine. So they take, I think generally like silicon, I want to say, something with silicon, I think, to kind of calibrate it before they start their NMR. So just ignore that. So here we have, okay, this is a 2 quartet, okay? And here we have a 3 triplet. All right. The formula for this one is C2H5Br. Okay. So, again, like I always, guys, always start off by drawing my carbons. First off, actually, the first thing you want to do is you want to figure out the geometry of your carbon. So far we've only been working with 2 carbons. So you know the 2 carbons are attached like that, right? There's nothing else to it. But like, you know, if I gave you like, you know, like C7H6Br3, right? You would want to go through here and you would want to say, okay, well, let me do my whole thing which actually this is a really good time to review it. Let's go back and do our whole geometry thing. So we need to figure out our degrees of unsaturation. So first what we're going to do is we're going to use this formula, CnH2n plus 2. So here we have C7, and H2n is going to be 2 times 7 plus, or 2 times 7 plus 2, so that's 16. And BRs, what do BRs do? I think they don't add anything, but let me just check. Yeah, no, they add 1. So here's the list. If you have halogens, oh man, my pencil ran out. You guys probably know what I'm talking about. This is just from Orgo 1. I don't think we've done it so far this semester. But basically, if you have a halogen, that's +1 hydrogen. If you have oxygen or sulfur, that's 0 hydrogens. And if you have a nitrogen, that's -1 hydrogens. Okay, so we have bromines, 3 bromines. So this is our formula that would be without 0 degrees of saturation. we have here, we have C7, we have H6 plus 3. What's 6 plus 3? 6 plus 3 is 9. Okay, so that tells us we have some unsaturation here, because we should have, if we had 0 degrees of saturation, we'd have 16 hydrogens, but instead we only have 9 hydrogens. So how many degrees of unsaturation do we have here? We have, let me quickly change this to an 8, because that would not happen. It's usually, okay. So, basically from this point on, we just need to figure out how many degrees of unsaturation. So, every time you subtract 2, that's 1 degree. That's 1 degrees of saturation. So in order to get from 16 to 8, that would be a difference of 8 hydrogens. So 8 hydrogens divided by 2 is 4. So there's 4 degrees of unsaturation. Are you guys following? You take like 16 minus 8 equals 8. 8 divided by 4, divided by 2 equals 4. So 4 degrees of unsaturation. So that tells us that there's either for like a ring, some double bonds, whatever. So I'm just going to make the bold assumption that it's this, right? With maybe like that coming off and then 3 BRs. So that fills everything. We have 1 ring and 3 double bonds, so altogether that's 4 degrees of unsaturation. Why do we divide by 2? Because we have to figure out how many excess hydrogens are needed, and then every 2 hydrogens that you don't have there is 1 degree of unsaturation. So we're trying to get to degrees of unsaturation, so I just divide them by 2. We don't have 8 degrees of unsaturation, we have 8 hydrogens missing. So that's every 2 hydrogens is 1, minus 2 hydrogens equals equals 1 degree unsaturation. So for every 2 hydrogens you're missing, there's 1 degree of unsaturation. All right. So why am I saying all this? Because basically before you start anything, you'll actually want, for more complicated cases, you'll want to go through and do this first. Maybe not later. You get to a point where the cyclohexanes are there, but maybe you want to double check it after you're done so you're not wasting time. But for now, whenever you see any like more complicated carbon structure, you're first going to figure out the general shape and write that shape down. So going back up here, we don't need to do that because this one just has 2 carbons. So I'm going to take my 2 carbons and draw them the way that they are going to be shown. And that's the first most important step. Next, we're going to start analyzing these hydrogens. We have 2 hydrogens that are quartets. So I'm going to draw 2 hydrogens. Let me do it on the other side so that it lines up. We have 2 hydrogens that are quartets. So these 2 hydrogens go here. And we know that across from it, there must be 3 hydrogens because it's a quartet. So this is going to, you're going to see this is starting to get really simple actually. And then that's it, we have 3 hydrogens that are a triplet, which makes sense. We have 2 hydrogens, which are a quartet, which makes sense. From then on, just attach your BR, because you know where that must be. Okay. So hopefully these should be looking a lot better to you guys now. Let's go on to a little bit more of a complicated one. So, I'm on page 8 right now. So for this one, he gives you your formula to start off with. He says C11H24. And I think I'm going to end at 7 o'clock because, NMR is one of those things, like if you just do it for 2 hours the first time you're releasing it, it's not going to be helpful to you guys. So we're just going to talk about it. We have still like another half an hour left, and then that'll be it for today. I think I'm going to end the session early, unless anyone has questions from the exam. But we can also go over the exam on Wednesday if you guys want. Okay, so here he has some peak, and this is a 5 multiplet. Okay, 5 multiplet. So that tells us that there's 5 hydrogens. And this is all the way, again, it's at 7. So we know that this is our aromatic ring. So that's a pattern you guys have seen before. So I can go ahead, I could draw my aromatic ring, and it tells us there's 5 hydrogens coming off of it. So we know that this thing must have, it can't be like pair, it only has one functional group coming off of the ring. Do you guys see what I'm saying? There's only one thing coming off of there, of the ring, because there's 5 hydrogens. So there's no way that there's like a bromine attached to the bottom, because there's 5 hydrogens. Okay, so next, once we've drawn our basic structure, let's go ahead. So we can see that like there is, here he has a 2 singlet, and here he has a, what is that? I'm like awfully confused. Oh, a 9 singlet. Okay, perfect. So drawing, let's continue down here. So we know that there is an aromatic ring with something coming off. We know that there is, so far we have 1, 2, 3, 4, 5, 6. Let's just say 7. So we have 7 carbons. So we actually have quite a few more carbons to go, right? So 11 minus 7, or let's just say minus 6. So 11 minus 6, so that tells us that there is 5 more carbons that need to be added on here. And at this point, I usually just go on the side and start figuring out the functional group separately. So a 9 singlet, that tells me it looks like this. That just, when you see a 9 singlet, it is always like that. Okay? No, not always like that, but generally. It's like, that should be something that you think of. So why do I draw this? Because there's 1, 2, 3, 1, 2, 3, 1, 2, 3. So that's 9 hydrogens all together. And they are all singlets because there's no hydrogen at that carbon. Okay? Don't worry if you didn't think of this right away. That's totally natural that you didn't immediately imagine it like this. But you will get there. So 9 singlets. So there's 3 hydrogens at each methyl. So this is basically a tert group this is describing. Then we have also a 2 singlet. All right, a 2 singlet could look like this because there's 2 hydrogens here, and that's also adjacent to only 1 hydrogen, or to 0 hydrogens, right? And what actually fits perfectly is if I draw it like this, then these 2 hydrogens here, they don't have any hydrogens adjacent on this side or on this side. There's no hydrogens adjacent to it. So it is really a singlet. Okay? Questions? All right, let's go. Next. So for this next example, it's a C4H. Let me get participants for this. So remember, we are recording, so if you don't want to be called on, just send me a quick little message. Because I want to start calling on you guys because I feel like a little tired of just doing the same thing for you guys while I'm the only one talking. So, all right. Let's see. Let's start with Ollie. You're appearing at the top of the list. So turn on your mic and do this one with me, if you're okay with that.
Yeah.
Okay. All right. So what do you think? Tell me what you're thinking. What's the first step?
You gotta check your saturation.
Perfect. Yes, exactly. So what, how do I do that?
So you have C4, and then you have basically H10 because of the two BRs.
Yes.
So then you have 2N plus 2, right?
Yes. Yeah. And that is
That is,
full saturation, basically.
yeah.
Okay. So now we know that there's no double bonds or any rings. So that could look a few different ways. It could look like this. It could also look like this, right? I think those are the only two options.
Yeah.
All right. So going off of that, what are you thinking now? This one's actually a little bit complicated.
I'm thinking it's going to be the second one.
The second one, okay.
Mm,
So let's start with the 6 singlet. So that tells us that there's 3 hydrogens on 2 carbons that are adjacent to a carbon with no hydrogens.
right.
That was like a really complicated sentence. Did you follow or should I repeat it?
No, I got what you're saying.
Okay, all right. So what do you think?
So would that mean there's a Br in the middle carbon?
Okay, smart.
And then there would be a Br basically on any of those branches.
Okay, but let's walk through quickly, like, so that we're saying out loud exactly what you're thinking. So what Ollie's thinking is, oh, okay, I'll make 6 hydrogens adjacent to 0 hydrogens. So that's our 6 singlet. And then he's thinking, if I put a Br here, that makes this 2 hydrogens also adjacent to 0 hydrogens. So a 2 singlet. Good job. Okay. Yeah, this is the correct answer. So again, at the end, always check your work, make sure that it follows through and it matches with the graph. All right, Destiny, you're next on the list. If you don't want to do this, then just let me know. But
okay, I'll try.
all right, cool. So C7H8O. All right. So the C7 thing. So I'm just gonna tell you, there's something going on here, all the way out at 7. It's a 5 hydrogen multiplet. So we can use M to like describe that it's a multiplet. So that'll usually be like 5 or more peaks will be a multiplet, because like it's just so complicated to like draw it out after that. Not really important. We also have a 2 singlet and we have a 1 singlet. Okay, this is also going to be a little bit complicated, but you'll get it. So what do I do first?
Okay, so we find the degrees of unsaturation.
Yeah, but that's not really necessary because we already have this peak here. And so we know something very important. What do we know? Remember, it's at 7.
What, that there's 7 carbons?
No, it's on 7 along the x-axis.
Oh, okay.
So what a peak there represents is it represents an aromatic ring.
Oh, okay. Yeah.
That has 5 hydrogens coming off of it. So what does that tell us?
Right, okay. Honestly, I don't really know. I'm kind of lost.
Okay, well, it says that there's 5 hydrogens coming off the aromatic ring. So that means that everything coming off of it in terms of carbons and stuff is only coming off of this 1 carbon. So that's kind of a place where it's important to start, or it's important to recognize that. Yeah. So what about this? We see that there's a 2 singlet. What could that mean?
A 2 singlet would be that that there's like, doesn't that mean that it's next to 0 hydrogens?
Exactly. So we have 2 hydrogens that are next to 0 hydrogens. And you did get like kind of hard one. This is the first one we've seen of this kind because we haven't added oxygens before.
Yeah, and that's where I'm like, where would we, is that where you put that line?
Our oxygen can't be right off there. I mean, unless it was like an ester, but that's not what we're dealing with here.
Okay.
I'll talk about esters in a little bit.
Okay. So yeah, we put 2 hydrogens adjacent to where there is 0 hydrogens.
Okay, so are you thinking like this, 2 hydrogens there?
Yeah, that could work.
Hydrogens. Yeah, because there's no hydrogens at the bottom, right?
Yeah.
And then the only thing that you don't really know here is that we can put our OH there. And this still counts as a singlet. This is still a singlet. because this hydrogen is different than if it was attached to a adjacent carbon. So that still makes it a singlet. It's basically there's no adjacent hydrogens. So that must be the part that you were confused at, because you were like, wait a second, that would be a doublet.
Yeah.
But it's not a doublet. It's still a singlet because that H doesn't count the way that other hydrocarbons do. So at this point, what about that one singlet? Do you see that all the way over here?
Yeah.
What do you think of this?
So that would also have to go. That would be one. Where would that go though? Because
Well, if you look at it, we already have everything down there. We have 8 hydrogens. Because we have
oh, yeah.
5 around here, and then we have 8 here, right?
Oh, yeah.
But what I'm kind of pointing you to look at is the fact that a one singlet corresponds to an OH.
Oh, okay, I see.
So that's just like a way to help you see the one singlet. Now, if you guys look very closely at your, like, again, we're on page 8. That singlet does not look like a typical singlet, does it? It's a tiny little bump. So short. Do you guys see that? He circled it at the bottom of page 8. Can anyone confirm? No one? Because this is very important for you guys to see. And next time I will have it so that I can show you guys on my iPad. But for now, like, I want you guys to open up the sheet from February 9th and go down to page 8. Okay, finally. So all the way at the bottom of page 8, and I will just draw it here just so you guys can see, but it shows 2 singlets next to each other. So I'll answer your question in a second, Melissa. Okay, so there's a 2 singlet that looks like this. It's very high. Then there is a 1 singlet, which is very, very short. Very, very short and kind of like wide. It's not like as like pointy as the other ones. So this is a classic OH. Anytime you see that little weird bump that's a 1 singlet, it's an OH. And yes, Lakshmi, really good point. So Lakshmi said, is the OH always going to appear around 3 or 4? Yes. So this is a classic way to figure out if there's an OH there. You see an O when you look at the original molecular formula. You see an O. So then you should immediately look for a little basic bump like that. That's an OH. It's very, very small, way shorter, way wider. And it's a 1 singlet. That tells you it's an OH. So the only thing I wanted to say is that it's not any time you see a one singlet. So let's come up with an example where there's such a thing as a 1 singlet. 1 singlet, what does that mean? It means 1 hydrogen that is a singlet. So we could easily do that. Let's say that I had something like this. So this has 1 hydrogen off of it. And then, let's say I put bromines here. That's a 1 singlet, right? So there's a lot of different ways you can have a 1 singlet. So it's not the 1 singlet part, it's the way that the 1 singlet looks and the location of it. It's around 3 or 4. It's very wide, very, very short. It's like a tiny little blip. Okay. It looks very different than all your other singlets. All right, next. Who's on my list? Okay, JD, your turn.
All right. What am I looking at?
You know what? We're gonna have to go to the next page. We're gonna have to go to February. So go to the exam 2 materials for your question. And let's go to February 16th. Okay, so we have Isabel. So just so you guys know, we're gonna be working from Isabel right now. So Dr. San likes to name all of his NMR review sheets after different students from his classes. So Isabel is apparently someone who took it a year before I did. When I took Orgo 2, there were only 4 people in our class, so he couldn't name it. Or no, not 4, like 6. So he has like 13, 14 huge review sheets that are like stuffed full of NMR, and each of them is named after one of his students. So you guys will also one day get some papers named after you guys. Does that sound good?
Oh, that's so fun.
Yeah. So here is Isabel. Also, when I was taking it, by the way, he had a few extra sheets, some new ones, And he was like, I don't know who to name these after. And we were like, after us. So he named like a Fatima, a Catherine, a Shahiq. It was really fun. So
That's so cute.
yeah. Okay, so here's Isabel though. And I remember this one. I was like shocked when he was like, here's Isabel. And I was like, what? Okay, so let's start. JD, you can start with Isabel, the first question on Isabel. So let me just like put it out first. So this is a 2 triplet. I don't see why there's a C there. Oh, but yeah, so a 2 triplet. A 2, 1, 2, 3, 4, 5, 6, 7. So on these ones, you're going to have to count. So you have to count each of the peaks yourself. 1, 2, 3, 4, 6. Okay, so 6. I think that's 6. Whatever. I'm just going to write it here. So this is a 2, 6. Inside the bracket is what I mean by like the number adjacent to it. And this is a triplet. Okay, do you guys see how you're going to have to read that and like figure out how many peaks are in it? All right, so what is this?
It's C3H7Cl.
Well, actually, you have to, walk me through it, because, like, oh,
yeah, I'm just saying, like, that's the formula he gave us.
Yes, and that formula is very important, because we can't figure it out without it. I mean, we could, but it would take much longer. So, what do you think we do?
I think you can see that there aren't any degrees of unsaturation because there's 7 H's and plus 1 Cl, which makes 8, and that's already 2N plus 2.
Yeah. So we just draw our 3 carbons, and now what?
And then we have to put well, there's 6 carbons on at least one of those, right? Or one of these is attached to has 6 carbons on either side.
No, not 6 carbons. 6 hydrogens.
6 hydrogens.
Let's call them beta hydrogens from now on.
Okay, let's call them beta hydrogens.
Yeah, I don't know if that's the correct, but yes.
And so that's the one in the middle, and we can see from the other one that that it's connected to only.
Wait, let me take that back for a second. It doesn't have 6 beta hydrogens; it has 5 beta hydrogens.
Oh, right, because it's
right
minus 1. Okay, so that's 5H. The one on the left would have a 2H, and so would the one that's furthest right. 2H.
No, one is 3. Oh, you mean beta hydrogens?
Yes, beta hydrogens.
Okay. Mm-hmm.
And so based on that, you can kind of tell that from the middle, one of the ones on the end is just going to be a methyl. It's just going to have 3 hydrogens.
Okay,
because
3 hydrogens.
It doesn't add up correctly otherwise. And so with the other 2,
well, wait. So at this point, you can already tell what's happening on the next one because you look at 3.
Yeah.
So you know that there's 2 here.
So I know that there's 2 there.
Mm-hmm.
And then by process of elimination, there have to be 2 on the one on the end.
Well, yeah, from there, let's just think about it. Let's go, okay. So first, I like to draw out one of my sets. So 3. This is a triplet, so I know there's 2 here.
Yes.
Now, let me examine those 2. Which one lines up with 2? It's either going to be our triplet or it's going to be our sextet. So it's probably our sextet, just because of the location. So what does that mean?
Right.
How many more adjacent hydrogens do we need? Beta hydrogens.
2.
We need 2 more beta hydrogens because we already have 3 beta hydrogens. So we need 2 beta hydrogens here. And that makes this a 2 sextet. So perfect. Now what?
By process of elimination, the one that's on the very end that is not a methyl has to have a Cl on it. Otherwise, it misses the octet rule.
Okay. So, yeah. So because we saw that there's a Cl left in our molecular formula, we know that the Cl must have been right there. Because it's the only one that doesn't, that has broken octet. And again, we can look at this one real quick just to check. 2, what would we call this? We would call, and sometimes, you know, like just cover up the rest of it and go through it. This I would call a 2 triplet. This I would call a 2 sextet because it has 5 adjacents. And this one I would call a 3 triplet. Let's go back up and check. We have a 2 triplet, a 3 triplet, and a 2 sextet. Perfect. Okay, so that's like another way you can check it. And then also, like, I mean, if you have more time, which on the exam you probably, if you get very comfortable with NMR, you will have extra time. So on the exam, you can look at it real quick and you can check, all right, do my hydrogens and carbons add up to the molecular formula? That's another last thing that you can do. 3 carbons, yes. 7 hydrogens, yes. 1 Cl, perfect. Done. Okay, thank you, JD. Good job. All right, Lakshmi, you're next. Okay, I'm gonna skip. I'm gonna skip to page 3 of Isabel, okay? Because I don't want to talk about the carbonyl group right now, because we're gonna be ending soon, and you guys have done a lot for today. I noticed you guys already getting more like fluid with the topic, just over us talking about it for like an hour. So good job on that. You guys weren't really answering the questions in the beginning that well. Okay, so question 3, page 3 on Isabel. Lakshmi, you're gonna be doing this.
Is this the C3H8O?
No, this is C5H12.
Hold on, I can't find it.
This is Isabel on February 19th. Oh, sorry, February 16th.
I can't find it, but if you draw it, I'll try and figure it out from that.
Okay. How can you not find? JD, could you help her? I just want to make sure that everyone can see this kind of stuff, though. So I'll draw it while, can someone direct Lakshmi how to find this?
If you go into Husky CT and you go into Exam 2 materials and you click on February 16 lecture, there should be one that's labeled NMR Isabel. You click on NMR Isabel. Are you there?
Yeah, I have it open. I just can't find the.
Oh, it's on page 3.
Yeah, it's the third one down.
I might just be blind. Wait, what was the thing again?
NMR
C5.
Isabel on page 3. It's C5H12O, and most of the page is just the chart.
I'm so sorry. I literally, I think I'm blind.
Wait, so did you go to page 3?
Yeah.
If you zoom out really far, maybe you can figure out where you are in the document.
Oh.
I think I'm just an idiot. Hold on.
Wait, which one are you seeing?
Okay, I'm looking at it at my notes, because I have the PDF downloaded and I had notes written on it, so I can't find it in my notes.
Oh, did you already do 16th?
Yeah.
Oh, okay, cool. Yeah, maybe just download it again. I don't know.
Yeah, it might just, it's my problem.
But that's fine because I have it up. I just want to make sure that you have it. So we're good. Okay. So I've written out the whole thing. So there's a 2 triplet. There is a 2 multiplet. I didn't really feel like counting it out, but usually you don't even need to. Like if there's like a multiplet, you don't need to really pay attention. We have this weird little bump here. We have a 2 quartet. Let me change that real quick. I wrote 4 by accident. This should be a quartet. And then there's a 6 doublet. All right, and you have the molecular formula at the top. So what should we do?
So there's no degrees of unsaturation.
Perfect. So it
Yeah,
could look like a lot of ways. It could look like this. It could look like this. You know, it could look like this. So there's lots of different ways it can look, but we will probably go through it to figure out which shape is best. So if I were you, I would just pick one of the random peaks and then just follow it through.
Honestly, I don't know.
Okay, why don't you start with, why don't you start with this one? A 6 doublet. So what does that tell us?
So that means there's 6 hydrogens that are next to 1 hydrogen.
Perfect. How does that look? That looks like this. So 1, 2, 3 hydrogens, 1, 2, 3 hydrogens. So that's 6 altogether, right? 6 hydrogens adjacent to 1 hydrogen. That's it. So this is kind of how you do it. You just slowly start piecing it together. So that is our 6 doublet taken care of. Now move on to a different peak. So at this point, what I would do, like what I just showed with JD, after I'm peaks that I chose to follow through. So this is a 6 doublet, right? That I just drew. Now I will just look at the one adjacent to it and follow this one through. This is a 1, a 1H, and this one must be a multiplet, right? Because it has how many adjacent
Yeah.
hydrogens? It has so many, right? Lakshmi?
Yeah. Yeah.
Yeah, it's like really a lot, right?
Yeah, there's a lot.
Yeah, exactly. So from this point on, we also know that there's so we know that this multiplet must be here, right? Because it's a multiplet, like it's 7, it's a lot.
Yeah.
So basically, we know that one of the hydrogens from the multiplet is this one, but there's another hydrogen that's very much a multiplet as well, is what it's telling us, because he said there's 2 multiplets. So there's another hydrogen that's a multiplet. And it's totally fine that you don't, like, you're not getting this completely. This is all new stuff. Like I hadn't described to you before how, you know, one of the multiplets might be in one position and another multiplet is in a different position. But they add up to 2 multiplets. So let's just move on. Let's try to tackle this one now, the 2 quartet. So what would a 2 quartet look like?
So it's 2 hydrogens that are next to 3 hydrogens.
Perfect. How about this? If I drew like this and there was 2 hydrogens here, these 2 hydrogens would need 3 hydrogens over here. Or sorry, 2 hydrogens on that side in order to be a quartet, right?
Yeah.
So there's these 2 hydrogens right here. Let me erase everything else. So these 2 hydrogens right here are now a quartet because they have one hydrogen to the left and 2 hydrogens to the right. So they're a quartet.
So then would the hydrogens that you drew like all the way to the left, like that are pointing down, would those be 2 triplets?
2 triplets. Wait, where?
The
Yeah, those 2. Okay, so those 2 are, yes, they're going to be 2 triplets. Yeah, where's the 2 triplet? Is there a 2 triplet? Yes, that's the 2 triplet all the way on the left. Sorry, I didn't even see it for a second. Yeah, that's exactly right. So these two are going to match up with this one right here, the 2 triplets. So that kind of follows through. That makes sense. From here, let's just review everything we have. So we've taken care of everything. The only thing is, what do you call it?
Oh, would you add an OH to that same carbon?
Exactly. Because that doesn't mess with the fact that this is a triplet, right? Because having this OH, this H here doesn't really mess with it, so that's perfect. So those two hydrogens are still a triplet, which is good. Yeah, the OH, so this H corresponds to what? This H right here. How did you know there was an OH?
The little like bump that's next to that's in
That,
between the two. Yeah.
yes, because sometimes we don't know. It could be an ester, right? Or it could be a carbonyl. But this little bump makes it known that it's an OH. Okay?
Yeah. So when he gives like next to it the multiplet, is he gonna tell us like how many there are?
Sometimes it's not necessary because like we finished all of this and we know that we have the right compound. So we don't really need to know how many were on that. And it would be really, really hard to count 7 little bumps. So when I saw, like, I looked at all those bumps and I was like, oh my God, that's so much to count. I'm just going to call it a multiplet. Sometimes he will give you the number, but really it's not necessary most of the time. You have all the other numbers, so you can figure it out. Yeah. So I think, because he said the 2 multiplet, so I don't really get that. I think he meant 1 multiplet, because it's kind of hard to see what's going on there. I think I'm going to change this to 1 multiplet, because I can only see 1 multiplet. Yeah. Because I couldn't quite figure out what the number was supposed to correspond to. All right, guys. So I think that's it for today. Does anyone have any like closing questions? If you guys watch, when you guys watch February 16th, he'll start telling you about carbonyl groups. Okay. No questions? All right, can I have everyone send their net IDs in the chat real quick? Oh, I think everyone got checked in already from Abarca. Okay, perfect. All right, thanks guys. You guys have a good rest or a good evening, and I will see everyone on Wednesday. And your quiz is pretty soon, so definitely don't fall behind with the NMR. Okay, get a head start on that lectures for February 16th. All right, good night, everyone.